Okay, everyone. Well, it is 9 o'clock, and so I want to officially welcome all of you to our fourth and final, for now, Virtual Public Astronomy and Observing Night. We're so glad to have all of you here, so glad that you could join us for the first time or again, or whatever it is in your particular case. My name is Caroline Roberts, and I am the Observatory Manager and Astronomy Lab Coordinator at the University of Iowa. And again, it's just so great to welcome you. Tonight, the wonderful Cole Dorman is going to introduce us to our astronomy topic for the evening, which tonight is galaxies outside of our own Milky Way galaxy and the types of objects that are in other galaxies. And then afterwards, Professor Casey DeRoo is going to tell us about his own research within the field of extragalactic astronomy, galaxies again outside of our own Milky Way galaxy and the types of objects that reside in them. As before last night, this event is recorded. Mute yourself, turn off your video, change your name if you don't want any of that captured. We will be sharing this online with people who weren't able to attend the event. For our first two evenings, we're going to, blur everything out, so no worries there. But for last night and tonight, we'll keep the recording as it is. So please do turn off your video and things if that's something that you would prefer not to have happen. Again, as before, I recommend that you turn off your video to help with connectivity, connect to Ethernet rather than Wi-Fi if possible if you're having connectivity problems. After Cole Dorman's talk and Professor Casey DeRoo's talk, there will be some time for questions. And if you would like to have a question answered, we highly recommend that you do pose it either over audio if you're okay with your voice being recorded, or posting it down into the chat box. We'll be doing our best to answer as many questions as possible down below in the chat. However, if you are okay with unmuting yourself, you might have a chance to skip to the front of the line for those questions. As before, we welcome you to like us on Facebook. And then finally, if you would like copies of the images that we take tonight, drop me an email. Some people have requested images from last night, and I'll send those out soon. Again, it's looking a little cloudy in Arizona tonight. So fingers crossed that like last night, it will clear up sufficiently for us to observe, but we'll have to wait and see what the weather is doing in an hour before we'll know for certain. Without too much further ado, I would like to introduce you all to Cole Dorman. He doesn't need introduction to most of you. I know a lot of you have been to previous nights, but I will tell you a bit about him in case it is your first night. Cole Dorman is an undergraduate physics and astronomy major at the University of Iowa. He's the president of the Department of Physics and Astronomy's Society of Physics Students organization. Let's thank Cole very much, and he's going to introduce us to our topic for tonight.
All right, hello everyone. Let me just share my screen real quick. All right. Tonight I'm going to be going over everything that is galaxies, starting with our own Milky Way, to all the different galaxy types, to even how galaxies fit into the structure of our universe. So without further ado, let's get started.
Yeah, I muted it.
No better place to get started than with our very own galaxy, the Milky Way. Like any galaxies, the Milky Way has a ton of stars. If our solar system out to Neptune was the size condensed down to United States quarter, then the Milky Way would be as large as the continental US, to kind of put in perspective just how large the Milky Way is compared to our solar system. Now, our galaxy, like many others, rotates around a supermassive black hole. Going from centered outward, there's a central bulge, followed by a relatively small bar with arms for our galaxy jutting out and surrounding the galactic center, creating a disk. There's also a galactic halo, which completely surrounds everything, and it's dispersed with tight-knit groups of stars called globular clusters. But our galaxy isn't unique, and there are many galaxies like the Milky Way. There are lots of galaxies nearby to us, but there are lots of galaxies that are really far away. In fact, if you take a telescope and look at a region of the sky that doesn't have much going on, with few stars and Milky Way in the way, of course, and just take a nice long exposure image with your telescope's camera, collecting lots of light from this dark area of the sky, hundreds of galaxies pop out in a single image of the dark sky. Very few lights in here are stars. The Hubble telescope did just that, what we're looking at right now, by pointing in a region of the sky smaller than the full moon, just in a direction of the southern constellation Fornax, also known as the Furnace. These are the galaxies Hubble saw in the dark sky, far beyond our Milky Way galaxy, and there are billions of galaxies in the universe.
Cole, may I pause you for just a second?
Oh,
I wanted to do a poll and I forgot to do it. Will you
don't
go
worry
back
about
a
it.
slide?
Oh, yeah.
Perfect. Okay, sorry for the interruption. I'm going to send out a poll to everyone. So there are a lot of galaxies in the universe. Which of the galaxies listed below, try to guess, is not a real type of galaxy?
Pretend you didn't see the earlier slide.
Your options are a circular galaxy, an elliptical galaxy, a spiral galaxy, an irregular galaxy.
You guys are smart. You're avoiding some answers.
Okay, 5 more seconds. Okay, it seems as though there's a general consensus that a circular galaxy is not a real thing. So listen on, pay attention to Cole, and learn if you all were right.
Might prove you right, might prove you wrong. I don't know.
Awesome, thank you, Cole.
So, there we go. We, the Milky Way, are what's known as a barred spiral galaxy, or an SBC galaxy to be more specific. There are 4 main types of galaxies, though. They're elliptical, spiral, barred spiral, and lenticular galaxies. To classify galaxies, they're given a specific letter, then either another letter or number depending on its properties. Elliptical galaxies have a smaller number based on how circular they are. And spiral barred galaxies have either an A, B, or C classified with them, depending on how tightly wound their arms are and how large their galactic core is. Finally, lenticular galaxies are always classified as either an S0 or an SB0. But what makes these galaxies so different? What makes these galaxies so different and unique? Well, let's start with an oldie but a goodie, literally. Elliptical Galaxy is the oldest galaxies in the universe, and because they're so old, they're filled with low-mass stars. If you remember from our June 13th talk, the smaller a star is, the longer it lives because it doesn't burn as much fuel as quickly. Besides stars, there's not much in elliptical galaxies. They have a pretty sparse, what we call interstellar medium, which is just the stuff in between. And unlike spiral galaxies, like us, whose stars move primarily in a disk, elliptical galaxy stars move radially, meaning they're not at all moving in a flat plane like how we think of our solar system. They're kind of moving in all directions. Elliptical galaxies are also typically found inside galactic clusters towards the center, which we're going to touch on in a little bit. Next are lenticular galaxies, which are sort of an intermediate between elliptical and spiral galaxies. Now, like elliptical galaxies, lenticulars are filled with old low-mass stars. Unlike ellipticals, though, their stars orbit on a disk similar to the spiral galaxies we were talking about. Oh, wait, yet to talk about. I lied to you guys. Unlike ellipticals, though, their stars, I just said that. Their disk has a fair amount of dust, but not much active star formation. And the final galaxy type is the spiral galaxy. Now, like we talked about before, spiral galaxies have a central bulge, followed by long arms that birth tons of hot young stars. A giant sphere called a galactic halo surrounds everything, which is filled with older, cooler stars. There are lots of spiral galaxies, making up about 3/5 of galaxies in the observable universe. And then there's a subsection of spiral galaxies called a barred spiral galaxy. Barred spirals make up over half of spiral galaxies, with the only main difference being the large bar that juts out before the arms attach to the bulge. Spiral bars are also what the Milky Way is. And there's some galaxies that are completely weird in and of themselves. So this kind of answers the Zoom poll earlier. Unfortunately, circular galaxies do not exist. But we do have an irregular galaxy, which is what we're looking at. An irregular galaxy is what you get if a galaxy just doesn't fit in any galactic classification type. There are about a quarter of all galaxies out there, but they tend to be pretty small. And they can come about from once being normal galaxies that just deformed under uneven external gravity, or it can come from two galaxies crashing into each other. Now, if you're able to make it to our talk yesterday, we talked about supernovas, neutron stars, and black holes. When the most massive stars run out of fuel, they collapse under gravity and explode into supernova, producing either a black hole or neutron star, depending on the star's size. Even though the Milky Way has hundreds of billions of stars, they're so rare that we just don't see them in our own galaxy. The universe is massive, though, with billions of galaxies that each have their own billions of stars. And so many stars, our brain isn't designed to comprehend it. With all this stuff, though, we're able to make plenty of detections from outside galaxies. We see here a supernova that occurred in the Cigar Galaxy, and the event here is known as SN 2014J. Now, a supernova occur in all types of galaxies. They're relatively uncommon, like I said before. And but in terms of the universe, there are so many galaxies out there, we can see them frequently. Now, every once in a while, we find two extremely massive objects, like black holes and neutron stars, orbiting each other. And if they collide, things become pretty crazy. So crazy, in fact, that it can warp the space-time around it itself. Now, what do I mean by that? I mean that if a pair of black holes or neutron stars, or one of each that orbit and collide with each other, create things called gravitational waves. Now, like how electromagnetic force travels like a wave through light particles called photons, gravity too can travel as a wave. It's a lot harder to detect, though, because gravity is so much weaker than electromagnetic force. We can kind of visualize it in our heads like this. Any object that has mass has gravity. If you put any two objects an inch apart from each other, though, they're not going to budge at all. They're not going to go any nearer from each other or anything like that. Take two magnets, though, and put them an inch apart, and you can see them pull on each other, just demonstrating how much stronger electromagnetic force is than gravitational force. Even though gravitational force is what pulls us on all the time, the Earth is so massive that we can visibly see the effects, and we're so small. Now, let me play the video. That's why objects need to have crazy mass to see gravitational waves, because gravity is so weak. We see here in the video that the two black holes approach, the ripples become faster and stronger. Finally, we'll see as they start to meet, they're going to create this big wave of gravity that's going to warp all the space-time around it. As they're getting closer, we can visibly see that these ripples are becoming more frequent and they become more potent. After a bit, they're finally going to collide, and then there's the wave pulsating out. Here's a photo. Next slide. There we go. Here's a photo taken of a gamma ray burst coming from two neutron stars colliding. The event of this gravitational wave is known as AT 2017 GFO. Not a very catchy name, I know. But that's not the only crazy thing we see come from black holes. Like we touched on before, most galaxies orbit a supermassive black hole. In some galaxies, there's a disruption of gas and dust surrounding a supermassive black hole. And some gas and dust falls in and the rest heats up and shines this incredible bright light around it. They pool up while orbiting the black hole, this stuff, and it creates something called an accretion disk. Now, accretion disks are moving extremely fast, and because they're moving so close to the black hole, and they're moving so quickly, All that speed and friction is what makes it so bright. The magnetic field of a black hole interacts with this accretion disk too. All this energy mixed with this powerful magnetic field spits out two beams of matter from the accretion disk, which go so fast that they approach the speed of light. This is called an active galaxy, and their cores have so much energy and are so bright that they can completely outshine galaxies thousands of times over. There are plenty of types of active galaxies depending on their age and the angle we view them at. About 1 in 10 galaxies that we know of are active. All this talk about galaxies though, but how do they interact with each other? You may have picked up earlier that I kept on mentioning galactic clusters. Well, even galaxies bind each other with gravity. Large galaxies can even have smaller galaxies orbit them, like how we orbit the sun. Actually, our own Milky Way galaxy has a few small dwarf galaxies orbiting us. A group of galaxies bound by gravity is called a galactic cluster, and the one we're in is named the local group. Makes sense to me. Now going a step forward, there are superclusters. We're in the Virgo supercluster, which in turn houses many other galactic clusters. Taking that a step further, there's the Lenticular supercluster, which houses the Virgo supercluster and a bunch of other superclusters. At this point, we're so far out, we believe there's only 10 million superclusters in the observable universe, in which you guys know 10 million is a lot to us, but in astronomy terms, it's relatively small. So finally, we have the one and only observable universe. This has everything we could ever see and everything we could ever imagine, and so much more. It's really hard to appreciate how massive the universe is. I hope this scale kind of on the left helps. Going from the Earth to the solar system, to the Milky Way galaxy, to a cluster, to a supercluster, to a super duper cluster, to everything itself, each time it gets exponentially larger than the next. And so with that, I want to thank you for being a wonderful audience. And I had a great 4 nights as we know it. And I now want to just start answering some questions for a bit. And so if you guys want to type out your questions in the chat, or if you want to unmute yourself and ask me, I'm happy to answer. All right. Oh, you know what? Hold on. I'm having a difficulty pulling up the chat. That's not good. All right. I'm going to stop sharing. Hopefully that'll make my life easier.
And there really aren't many recent questions. So
oh, there aren't. Well, thank you, Ed. Anyways, but
do your thing, audience. Any questions at all?
And don't be shy to ask questions later. I try to be pretty active in the chat whenever Professor DeRoo and Dr. Roberts is talking. So.
Well, maybe no questions tonight.
Oh, somebody's raising their hand.
Oh, someone's raising their hand.
Zarish, if you'd like to unmute yourself, you are more than welcome to. I promise you, there's no line here. So.
I'm interested in all of this, Lanikia, but I thought Lanikia was the furthest we could go because dark energy is not letting any of the superclusters go. So, they're so far away, that like you can't reach one another.
That's true. You know, it is pretty hard to get from one thing to another.
We can't even. It would be really hard to get to the next supercluster, and it would be like, so how hard would it be to like colonize the whole universe?
How hard would it be? Well, let me tell you, light is the fastest thing in the universe. Nothing can go faster than light. And these things are millions of billions light years apart from each other. A light year is how far it takes light, or how far light goes in 1 year. If it's taken light millions of billions of years to go, man, I'm not a very fast runner. There are a lot of fast runners than me, but it's gonna be a while. I don't think with our current understanding of what's going on, I don't think it'll be possible to ever get to another supercluster or anything like that. Somebody asked, was slide 16, they asked me privately, was slide 16, I can't talk, an artist drawing or was an actual picture from the Hubble? That's a great question. I don't remember what slide 16 was, so I gotta look. Oh, it looks to be an artist's conception. It does not look very real to me. Maybe I can share my screen again. Here, yeah, this is slide 16. Those who are curious. I do my best to credit all the images, but it appears this one just kind of slipped from just a mistake I made on accident. So I can go back and I can let you know a little bit later where this comes from. But I'm pretty confident this is an artist's depiction of an active galactic nuclei. I'm going to stop sharing again. How many galaxies, did you say how many galaxies humans have observed to date? Quite a lot, quite a few. I cannot deliver you an exact number because I bet it's growing by the second, but a very, very large number. I'd say easily in the millions. You know, we just look at that picture with this exposure time, and there's thousands of galaxies in that, more than I could certainly count in one sitting. Maybe if I put, but there are a lot of galaxies out there.
And someone also
somebody
asked how many galaxies there were, and so that's in the hundreds of billions. But just as Cole said, you know, we've only imaged probably in the millions. But just from just knowing the size of the universe and a good understanding of our nearby universe, we can then say, you know, with the number of galaxies that we've imaged, we know that in truth there are hundreds of billions of galaxies throughout the entire universe.
That says my internet connection is unstable. I just want to let you guys know if I'm like cutting out random, promise I'm not being rude, anything like that. I can't control it. Somebody asked a private question, would other types of galaxies be more or less likely to have planets than spiral galaxies? Well, spiral galaxies are full of really younger, hotter stars, and elliptical galaxies are a lot older, have lower mass stars. And so we really don't actually know a lot about exoplanets, planets in other systems outside of the Milky Way galaxy. I don't believe we've been able to observe any outside the Milky Way galaxy, but I think it's a pretty safe assumption that all galaxies would have exoplanets. I don't think there's much unique about our galaxy other than housing Earth with all the life. And so I would say that other types of galaxies would be just as equally likely to have planets. However, I don't have the experimental data to back it up. Someone asked, does a spiral galaxy begin as a cluster of stars and then spread and flatten due to rotation? That's a great question. That's really touching on something called angular momentum and conserving angular momentum. Angular momentum is just really the angular speed and all of that, kind of how something's moving, you know, the amount of oomph that something has when it moves in a circular motion. Whenever these galaxies form, angular momentum from all these different objects is going to be kind of canceling out with each other. Then eventually one direction is sort of going to kind of win, and that's the direction it spins. Over time, it sort of flattens out from all of this, just from like the spinning over time, kind of like how you like spin a pizza, the dough will go like that. And so I hope that's well, so I guess, you know, I didn't answer your question too well, being a cluster of stars. I think that it would be best to say that it starts out, it's a little complicated, but I think really at the core of it, it all starts with this supermassive black hole that can sort of be able to collect and be able to hold in a bunch of different stuff from its gravitational pull. And so it's a bit tough to do that, to have that large gravitational pull with just a few stars. Even though a few stars is a lot to us in galaxy scale, it's quite tiny. Someone asks, what is the fewest elements to qualify as a galaxy? That is a great question and a definition that I am unsure of, but I do know galaxies can get a lot smaller than our galaxy. There are these things called dwarf galaxies that we were talking about. They're quite tiny, and kind of like how we orbit the sun, how our planets orbit the sun, these dwarf galaxies orbit these larger galaxies. And so galaxies can get a lot smaller than the Milky Way and get a lot larger too. As for the fewest elements, I think that really as long as you have that large core that's able to hold in a bunch of stars, you would, at bare minimum, become a dwarf galaxy. Someone asked how many stars, and Dr. Roberts cut me off if I'm going over time or anything like that.
No, yeah, you've still got a couple minutes.
Oh, perfect.
I saw one other question. I think, were you just about to answer one?
Oh,
you go ahead.
I was, but I have a few minutes, so I can certainly, and I can type out answers in chat too.
Okay. I just saw one that we skipped over, which is someone asked what's the best time to observe the Andromeda Galaxy.
Oh, that's right. I saw that, and it totally skipped my mind.
Well, the Andromeda Galaxy is actually named this because it's in the constellation Andromeda. So in our Milky Way galaxy, there are, a number of stars. A few of them make up this constellation Andromeda. And back behind the stars in the Andromeda constellation, outside completely of our Milky Way galaxy, where the Andromeda constellation stars are, this galaxy is outside of our galaxy, the Andromeda Galaxy. But it just so appears that it's near to the stars of the Andromeda constellation. And so the Andromeda Galaxy is in the constellation of Andromeda. So in the late winter, early springtime, when the Andromeda constellation is up in the sky, that's a good time to see the Andromeda Galaxy. And then also, observing it on a night when the moon isn't too bright also helps. But that's the best time of year to see the Andromeda Galaxy. But Cole, maybe take one or two more questions that you want to answer.
Right. I'm just gonna keep on going in order, but I promise I will do my best to get to everyone's question. Someone asked, how many stars in the Milky Way galaxy? Sorry if you answered this already. You don't have to be sorry. I actually have to do this for my degree, so this is good studying for me. So ask away. It's perfect. I think it really depends on who you're asking and how they're evaluating it. There are a bunch of different tests or different methods of kind of trying to see how many stars in the Milky Way galaxy. And so I can't really give you an exact number because everyone's pulling out their own different numbers. And it's really hard to kind of nail down. But I'd say easily hundreds of millions, billions of stars.
Hundreds of billions,
lower.
Sure.
Yeah. But it really, it just all depends on who you're asking. So I guess the final question I'll do is, did Hubble help us locate more galaxies that we could identify from Earth? Yeah, they really did. On Earth, it's kind of tough because we have this atmosphere in the way. That's nice because it helps us breathe, but it blocks a lot of light from coming in. It gets all distorted from the clouds, from all the water we have in the atmosphere and stuff like that. And so to be able to kind of take a telescope and then put it on a satellite where we don't need to worry about any atmosphere, any city lights or anything like that, we're able to identify exponentially more than we ever could on Earth. And that is it from me, but I will be getting back to answering your questions. I'm just going to be muted.
Okay. And thank you one more time to Cole. He's given talks on every evening of these outreach nights, all 4 nights. He actually won a grant in the University of Iowa Department of Physics and Astronomy in order to be able to give these talks and do this outreach work this summer. And I'm just really glad for all his work and all his help. I would like to introduce you all to Professor Casey DeRoo. Professor DeRoo is on the faculty in the Department of Physics and Astronomy at the University of Iowa. He works in X-ray astronomy, both observational and instrumental. Professor DeRoo's research focuses on objects outside of our own Milky Way galaxy, including supernovae, the end result of the life of some stars, and active galactic nuclei, the active centers of some other galaxies. He also designs X-ray instruments needed to make observations of these objects. Please welcome Professor DeRoo.
Hey everyone, can everyone see my screen? Over here. Hi, I can see some of you waving. Thank you so much. And Cole, thanks for the awesome introduction. I'm not gonna lie, you did steal my thunder a little bit on the Hubble Ultra Deep Field. So we'll go back there, but it's okay, it's perfect. It's a great introduction because what I'm gonna actually talk about tonight is my research as it pertains to supermassive black holes in the center of galaxies. And in particular, galaxies outside our own Milky Way. And so I saw a number of questions about black holes in the chat. Happy to answer those after we talk. But to start things off, I wanted to show you a pretty picture here. So this is an artist's conception. This is actually Nico Maserati on behalf of the LINX team, which is an instrument collaboration that I'm a part of. And so this is an artist's conception of what it would be like near the event horizon of a black hole. You can actually see the distortions of space-time itself, like Cole was talking about, around that black hole. And so I think of myself as an X-ray astronomer in particular. And so that might sound a little strange to some people. We think about observing the stars with light that we see with our own eyes, right? We would call that optical light or visible light. But the universe is actually bright in a whole variety of wavelengths. And so let me show you a picture of what we could see if we could look in the X-ray at the sky. And so here what I'm showing you is a specialized instrument that was launched in the 90s. It's called ROSAT. And can you all see my mouse? Yes? No? Great. So here I'm showing you a picture. And so imagine, we have this sphere as we look out at the night sky. And because of the horizon, we can only see half that sphere at any one time, right? But if you think of that sphere just like you would think of as a globe, well, astronomers need a way to look at that as they would look at a map, right? Where is it in the sky? We want to map that out. And carrying around a sphere is really inconvenient. We prefer a two-dimensional map, a piece of paper. So imagine this as though we took a globe or we took the night sky and unraveled it here. And so then you can see where things are in all directions. And these, this red light, green light, and blue light here are different energy X-rays. You might think of them as different colors if we could see in the X-ray. And so one thing that I find really exciting about X-ray astronomy, and so also some of you are thinking like X-rays, are these like dental X-rays? Yes, that's exactly what we're talking about. So we're talking about the same kinds of things that when you go to the dentist, you get an X-ray to see your teeth. It's exactly the same kind of light that we are observing the universe in. So one of the reasons I like studying X-rays is it's home to a number of really exotic and energetic events. So supermassive black holes, the explosions of stars at the end of their lives, we call supernova. These are all objects that are bright in the X-ray, as well as really, really hot gas. And so when we're talking really hot, we're talking about millions of degrees Celsius. I mean, gas that doesn't exist, we would think of this as a plasma if it were here on Earth, right? It's so hot that it doesn't even really qualify as us talking about gas. And so the sky is bright in X-rays, and we can really focus in on some of these really exotic objects that get us excited, like supermassive black holes. So carrying on here. And so one of the other things here, when we're talking about these exotic objects and X-rays in particular, is that me as a scientist and as an X-ray astronomer, what I'm really studying is gravity. So X-ray and the X-ray phenomena that we observe are powered by extreme globs of mass that are accreting material and bringing it in from very large distances. And there's a lot of energy released there. Just like, it's really hard to accelerate a baseball, right? But if you drop that baseball off the Empire State Building, it has a long way to come in. That's a lot of gravitational potential as it's being sucked towards the Earth. It gets a lot of speed, it would heat up. And so that's the kind of energy that we're looking at and we can see in the X-ray. And so here, this is a simulation, so not an artist's conception and also not an observation. This is us plugging in as much as we know about physics into a computer and then simulating what we might see. And so to give you a sense of scale, Cole talked about the Laniakea supercluster or the Virgo supercluster. So this is a simulation of what the Virgo supercluster might look like from a distance observer in the X-ray. And so you can see here that we've got huge bunches of mass here that are emitting in the X-ray because that gas has fallen in from a large distance towards this big massive galaxy right here and gotten really hot and started to emit X-rays. One of the things that's exciting about working in the X-ray as well is that we study matter in its most extreme state. And so I mentioned earlier briefly, it doesn't even make sense to talk about some of this material as gas, but as plasma. And so what we mean by plasma is material that's so hot that the atoms themselves have become protons and electrons separately. They're not the elements that we think of that are electrically neutral. Instead, we've got protons flying around that would normally be in the nuclei of atoms. And we've got electrons flying around that would normally be orbiting those nuclei and are now free to move around. And so here I'm showing you one of the most beautiful images, I think, personally in astronomy. This is a picture taken by the Chandra X-ray Observatory of the Taiko supernova remnant. So Taiko was actually a supernova remnant that we watched go off historically and took observations of it at the time with our eyes. Now, in the X-ray, we can go back there literally 400 years later and look at the aftermath in the X-ray. And so this is what we're seeing. These are the guts of an exploded star, and that plasma that's superheated and separated into its constituent elements of protons and electrons. So really, really hot stuff. And then finally, one of the cool things about these extreme objects is they don't just keep that energy close by, they feed that back into the medium that surrounds them. And so what I mean by that is maybe best illustrated by this picture. So this may not look like much, but what I'm going to tell you here is that at the center here is a huge elliptical galaxy, right? So in this picture right here, there's an optical image, a radio image that you can see here in red, and an X-ray image that you can fairly faintly make out in blue. So if you could look at just the optical image at the center here, you would see a massive elliptical galaxy. And this is hundreds of trillions of solar masses. When I say solar masses, I'm talking about the mass of the sun. So we're talking about a galaxy here that's like 100 to 1,000 times more massive than our own Milky Way. It's huge. And at the center of that galaxy is a huge supermassive black hole. Now, what's incredible is that supermassive black hole, as material is falling in on it, it doesn't all get globbed on. In fact, that supermassive black hole will send feedback. It'll punch out. And so it's actually punched out over millions of years, these huge holes. These holes are bigger than the Milky Way galaxy themselves. These holes are about 6 Milky Ways across here. In other words, it would take light 600,000 years to move from here to here in this image. This is massive. And it's all being impacted by a relatively tiny supermassive black hole at the center of this huge galaxy. And so here we see that supermassive black holes not only impact their immediate surroundings, they impact other galaxies. They've expanded beyond their own host galaxy to impact other galaxies. So all of this we can study in the X-ray. And so that's one of the themes that I want to bring forward in my talk, is that X-ray astronomy, if you were not aware, right, that astronomers use X-rays to actually look at our universe, I want to convince you that this is a really important window for us to be able to go look at these energetic processes that are happening within our universe, whether they're supermassive black holes or supernovae. The other thing that I would like to give you as a takeaway for, oh, hang on, I'm skipping ahead here. So final point about X-ray astronomy and why it's cool. I'm going to show you a quick video. So this is also a simulation. And it's a simulation, if you can imagine, of two different universes. So what we do is we take all of the physics and all of the astronomy, all of the science that we think we know, and we build models of the universe like we think it should work. And then we let it evolve over time, and we can take snapshots and see if it looks like the universe that we observe, right? This is the way that science proceeds fundamentally. We have a model that we compare with data. And by doing that, we can tell, is this a good model or is this not a good model? So in this case, I'm showing you a couple of different images. So I'm showing you the total amount of gas here on the left. That gas's temperature here in this column right here. This is a column showing you what kind of stuff is being produced by stars. And then finally, I'm going to pause it here and get rid of the YouTube pop-up. This is finally showing you, if you looked out in the universe with just using your eyes, what would you see? And so one of the key things that I want to show you here is that X-ray astronomy offers a really unique window. So step back for a second. Which of these windows looks the most different? There's different physics here, and there's different physics here. But I would argue that this is where you can really tell the difference, right, in terms of this gas temperature. In fact, if you have to depend on only your eyes, you're trying to tell the difference between this picture and this picture, which you can do, but it's hard. It's really hard. So this is the starlight that we would see with our eyes. But this is the picture that we get in the X-rays. This is telling us what the gas temperature is. And so this is a really unique probe for us to be able to tell the difference between models that have this physics and models that have this physics, and be able to tell us what kind of universe we actually live in. Cool. All right. So another thing in terms of working in X-ray astronomy is that I appreciate is that it's a really young field, comparatively speaking. So we humans have been doing observations of the night sky with our eyes for thousands of years, right? I mean, essentially ancient cultures were developing astronomical techniques. But in the X-ray, we actually have to get into space before we can do that observation. X-rays don't like to pass through our atmosphere, and so we really needed rockets to get above the atmosphere and be able to observe the night sky in the X-ray. And so this is a really crude plot of the first X-ray source ever discovered, called SCO-X-1, which is in fact a black hole. And so the way that this rocket worked is you essentially have a rocket and it shoots up and comes straight down. It's almost ballistic, right? So all you're really doing, you're not going into orbit like the International Space Station or a satellite. Instead, you're just getting up over the atmosphere long enough to stare at something, make a quick observation, and come back down. And what this is showing you here is that rocket, as it was flying, saw something here. And then this is a background detector that's looking in a different direction. So that this is representing, hey, in this part of the sky, I see an X-ray source. This is what we started with. And this is the birth of X-ray astronomy, something like 55 to 60 years ago. And so there are people alive today working in my field who remember this experiment, which is pretty wild to me. You couldn't say the same thing about optical astronomy. Cool. So we still use sounding rockets today. And in fact, we use them in our research quite frequently. So I have a video actually of what one of these sounding rockets looks like going off. So here, if I play this and pause really quickly, and it goes. So be ready, it's fast. This here is a rocket on a launcher out in the desert of White Sands, New Mexico. There's no one around, so you can't hurt anybody, right? And here, to give you a sense of scale, this is a truck here. So this is about 40 or 50 feet tall. This is a big, big rocket. And in the middle here, this little white casing, that's our experiment. That's our telescope that's going to go look at the night sky. So you can hear the countdown. It goes. That's the first booster. You'll actually watch it go dark. And there's the second booster lighting, so that it can actually get all the way up above the atmosphere. So it gets about 250 kilometers above the. So we still use these today. 60 years later, we make observations with both satellites, but also sounding rockets to be able to test out technology. Oh, so I don't have enough time really to talk about my research in developing the new technologies that you might fly on these sounding rockets, which is really the basis of my research. But I can show you some pretty pictures of some really cool X-ray mirrors that have taken a lot of time to develop. These are made out of silicon. So think the same kind of silicon that's in your phone that makes computer chips. We actually make X-ray mirrors out of silicon now for the most part. But what I want to offer is we are working all the time, right, on moving from these old plots where we just had a hump indicating that there was an X-ray here, to these really fancy mirrors now that now let us image the sky in X-rays so that we can see particular sources and make out the structure surrounding a supermassive black hole. So I want to paint for you a picture of what we can do with advances in instrumentation, thinking about that X-ray astronomy offers us a unique window, and that instrumentation is really key to making new scientific insights or opening new fields like X-ray astronomy. So Cole talked about this, right? Cole talked about the Hubble Ultra Deep Field, right? So one of the stories, the way that this goes, is that the way that the Hubble Ultra Deep Field was initially formed was that there's a sign. So normally to use Hubble, you would propose for time. You'd say, I have this really interesting object. I think it merits some Hubble observation. I'm going to write a proposal. Here you go. Please, please, please give me Hubble time. And most often you do not get Hubble time, right? But there is something, if you run the telescope, called discretionary time. So these are the people who are like, oh yeah, okay, so Hubble should observe this, and Hubble should observe this then, and they make the planning decisions surrounding the telescope. But they have a little bit of time to be able to use every year to go do something interesting that's big that can't be encompassed in one proposal. And so one year, they got this wild idea. What if we just stare out into space? There's nothing there. We're going to pick somewhere that's intentionally dark. We don't see anything in particular there. We're just going to stare. We're going to stare for 12 days. So you can imagine like looking at a spot on the wall for 12 days and how boring that would be. And yet Hubble slowly brings into focus this beautiful, beautiful picture. So to give you a sense of scale, right? Cole talked about this is smaller than the moon. It's actually way smaller than the moon. So if you hold out your pinky at arm's length, this is about a degree. And this works whether or not you're a child or whether or not you're an adult. Turns out we scale kind of the same way, right? So if you hold it out at arm's length, that's a degree. And you can cover the moon with that for the most part. This is 1/100th the size of the moon. 1/100th the size of the moon. Way, way smaller than the moon. And yet there are 10,000 galaxies in this image. Some of the galaxies, some of the most distant galaxies in this image, we see only 600 million years after the Big Bang. I mean, when the universe was young, right? So what's incredible about this is that we see lots of galaxies, but scientifically, there's a problem here. We see lots of them, but some of them are right on top of each other. And it's really difficult to tell where this galaxy ends and where this galaxy starts. So this problem is only going to get worse. You may have heard about a telescope called the James Webb telescope. So Hubble, right, the telescope we all know and love, made that last image. Anybody have any idea about how big Hubble actually is in terms of a mirror size? Any guesses in the chat? It's hard to tell because I'm not standing in front of you. Deck of cards. Good guess. Much bigger. So I'm going to back up. Well, you probably can't see me. You can see my slides. It's about as tall as me, right? It's a little taller. So think maybe 2 meters in size, like a person, an adult person, right? James Webb is that big. It's huge. Now, as you get a bigger and bigger telescope, that means you have more and more light collecting area, which means you can see further and further back in the universe. That problem of not being able to separate galaxies that are on top of each other, oh, it's about to get a whole lot worse. This is what a simulated field of James Webb looks like, right? You can see here these tiny pinpricks of light, but there's also these massive elliptical galaxies that drown out in terms of contrast what we would see around them. We have the same problem in the X-ray. So James Webb will be able to see really, really far back in the universe. They can see really distant objects, which in astronomy means that you can see objects that are really, really old. In the X-ray, what we want to do is understand how black holes came into existence. We have some ideas about how they came into being, right? But as Cole mentioned, we think almost every galaxy has a supermassive black hole in its center. And we can actually see that at a very young age, supermassive black holes were already supermassive. Now, this is a problem because most of the black holes that are born in supernova are not very big. They're like 10 times the size of our sun. That's actually pretty small in terms of a black hole, right? But we get black holes that are all the way to a billion times the size of our sun in terms of mass. And it happens really fast. How does that happen? We actually don't know. And it's really hard to see. It's not like we can watch these things form with the current generation of instrumentation. Spoiler alert, the next generation of instrumentation, we're going to be able to watch that happen, which is cool. So we have a problem. We need to model. And we need to know how they evolve with galaxies. Like I was talking about with this supermassive black hole, this is impacting all the galaxies around it, right? So if we really want to understand how the universe came to be, how supermassive black holes evolved over time, we need to observe them in addition to their host galaxies. We want to see what James Webb has to offer us and what the X-ray has to offer us. So we need a next generation X-ray telescope that'll actually be able to do those measurements of black holes in their baby state. It's not enough, though, to be able to throw up any old X-ray telescope. We actually need one that's got really, really good eyesight. So to give you an example of that, this is the field that we would see from James Webb. This is giving us our galaxies. This is an X-ray image that's giving us our black holes, right? So each one of these dots is a black hole, and in purple here, these are the black holes that are in galaxies in particular. But if you're trying to tell, does that black hole belong to this galaxy, or this galaxy, or this galaxy? It's really tricky, right? You have a hard time identifying what this spot, right, what this blur is home to. Contrast that with a telescope that we want to launch for Lynx. This is a nice little tiny dot associated with a nice little tiny galaxy. This is what's going to let us actually look at those baby black holes in their little cradles, in their galaxy cradles, and be able to understand how they became so big so fast. So this is what we need to do for the next generation of X-ray observatories. And this is what I would say work on every day, but like it's slow going, right? So this is what we're working towards, right? But like I mentioned, this is really cool. So a lot of you will have seen this image, right, of this supermassive black hole in a galaxy that we call M87. This is a huge black hole, but black holes this size actually already existed really, really early in the universe. So what we're really talking about is making a telescope that will let us walk through from distances, right? Much farther away to much closer, which is kind of like watching a movie, right? We can actually watch now at different times. We can observe things that are really far away. We can observe things that are continuously closer. So that lets us actually watch black holes grow from these tiny babies into these monsters that we observe today. And I actually just had a baby, and I have baby language all throughout this talk, so I couldn't resist like watching this tiny baby. This is my baby. This is Philip. He's about three weeks old at this point. Yeah, he's real small. But watch these babies grow into monsters, right? So with that, that ends essentially what I focus on in terms of research. Go Hawks, the Hawkeye symbol there. My email and lab web address are down here. I'm also on Twitter. If you have a question later on or want to chat, feel free to drop me a line. I'd be happy to talk. And with that, I'll turn it loose for any questions. I'm seeing some accumulate in the chat.
Wonderful. Thank you so much.
So one of the questions that I saw earlier, and this is a real throwback here. Joshua McNary, I think, asked, how far is the event horizon in light years? Cole, did you have a chance to answer that?
Yeah, it really depends on how much mass a black hole has. So every black hole is different. And so all black holes at their core are just a singular point. They have so much gravity that their self-gravity collapses themselves down further and further, infinitely down to a singular point. But even though they're all singular point, they can vary in mass. And so the larger the mass there is, the more of a gravitational pull there is, the more of a sphere of influence. And so the event horizon is going to be a little bit larger out. And so it's kind of difficult to answer how many light years there is until event horizon, because there are just so many different black holes out there that there's not really one specific set answer. It would be like asking, like, what's the radius of planets? You know, there are tons of different planets out there. I don't know the radius of, it's impossible to answer, I guess, the singular radius of all of them.
Yeah, so Cole, so you've touched on the key element, right? Which it depends on mass. So A for the day. Nice work. Yep, good deal. One of the things though that I do want to answer, right, is, so Cole's right. It depends on mass, but they're actually a lot smaller than you think. So for an object as massive as the sun, if you were to shrink it to a black hole, it would be about 3 kilometers in size. You can run a 5K in a black hole, right? For a one mass supermass, or for a one mass black hole, and it grows linearly with mass. So even this black hole here, we wouldn't measure in light years. It's actually much, much smaller than that. We measure the typical size for like a supermassive black hole is about the size of our solar system, which is pretty wild. How and who first thought to apply X-ray to astronomy? That's a great question. So that rocket experiment is actually done by Giacconi, Riccardo Giacconi, who's an Italian immigrant to the United States. And he sort of had this, this vision of applying, doing X-ray observations with rocketry about that time, in the 55 to 60 years ago. And so he actually won a Nobel Prize for that, for the birth of X-ray astronomy. So I guess I would credit him as probably being one of the founders. There's also, though, a lot of influential thinkers in this point. So for instance, telescopes, it's actually really hard to design an X-ray telescope. They don't work like the telescopes that you and I are familiar with on the ground. So it turned out you needed a special optical design that was thought of by Hans Walter, who's a German and published a pretty influential paper in 1952. it also goes even further back. We sort of figured when we postulated the existence of black holes that there would be associated emission that would be high energy. And so that would be, of course, X-rays. So it's probably a difficult question to identify the first person, but there are some big names in the field, and Giacconi is certainly one of them. He's got a fascinating story. It makes for a really compelling both science read, but also an American read. You're thinking about someone as an immigrant who helped shape a huge portion of U.S. astronomy. So Jim asks a great question. So if black holes crush matter into a singularity, that suggests the space between atoms is compressed. Do we also believe that a black hole crushes the space within an atom? If that happens, doesn't that also result in a large emission of energy like a nuclear bomb? Absolutely, yes. And so when Cole is talking about a singularity, we're talking about a point. It has no space. We're talking about crushing everything down to an infinitesimally small, like not definable point, right? And so we're crushing that space within an atom. To give you context, right, about how much energy that releases, because you're exactly right, that would release a ton of energy. So I showed you this picture, right, of this supermassive black hole that's blowing out these huge cavities. The amount of energy that it takes for you to be able to blow out those cavities is a unit that we call, is measured in a unit that we call ergs. So I think of this in terms of ergs because I've been trained this way. So this is 10 to the 62 ergs. But I did a little math before I came here to try and put this into perspective here. So a nuclear bomb, right, releases about 10 to the 20 ergs. And so for scale, if since the start of the universe, we had let off a trillion atomic bombs per second, that would be enough energy to equal the output of this one supermassive black hole. A trillion atomic bombs per second for the life of the universe. That's how much energy is contained in this. It's insane. I mean, it's insane. So yeah, there's a lot of energy to be gained from that gravitational infall and compression into that really small space. How does the rocket stay above the atmosphere before dropping, or how long does the rocket stay above the atmosphere? Do we have a way to aim the camera up to a particular place before the rocket returns? I'm over time, Carolyn, sorry. So this will be my last question. Is that okay?
No, that's more than fine. In fact, I'm in conversation with the observatory director. They're having a little trouble opening their roof tonight. So
cool.
You currently have as much
time. I will
time.
continue to answer questions for the next 5 minutes or so.
Yes, and
Cool.
if at any point in time you're
Awesome.
done, just let me know and I can take it over.
Sounds great. So the rocket flight is actually about 5 minutes. It's short. It is real short. And so it makes it really important to be able to get up above atmosphere, open everything up, and get on target. So I did not do this for my PhD, but I know a lot of people who did. So there are lots of people that got their PhDs doing sounding rocket flights. So they design an instrument from start to finish and launch it. And let me tell you, that is the most stressful 5 minutes of their lives. They're watching something that they've worked on for years in space at that moment, and it could all go wrong. It's stressful. So, but luckily, there is a way to aim the camera. So NASA actually provides, so we show up with the instrument, right? We have the easy part. NASA actually provides the rockets, and they provide a system that you can think of as sort of like a spacecraft bus. And so that system handles all of the data transmission from space to Earth. It also handles what we call attitude control, or so that's essentially how you would point at the night sky. And so you can think about this rocket as going up, steering around and looking around with its attitude control, and then it gets on target, and it does that within a couple of seconds, and then it observes as it's kind of drifting up in the atmosphere, just like a bullet or just like a ball that you might throw up, stays on target, and then transitions to falling back down. It's real short.
Wonderful. Okay. If there are any more questions, feel free to ask them, but otherwise we can transition over to the observing part of the evening. I want to thank Professor DeRoo so much for his talk tonight, and I know that everyone joins me in thanking him.
Thank you all so much. You guys were a great audience. I really appreciate the opportunity to share, what I work on a daily basis with you all. So, and please feel free, don't hesitate. Both Carolyn and Cole have my contact information. If you have other questions, please feel free to drop me an email or send me a message. I'd really appreciate it. So I'm gonna go grab some sleep though, because I've got a newborn. Bye-bye all.
Wonderful.
Thank you.
Take care.
Thank you.
Okay. Well, everyone, you get to see, again, a little bit of troubleshooting in action in a minute here. The Iowa Robotic Observatory, as I've shared before, is located in Sonoyta, Arizona. And so there's actually a retired couple who run this observatory as their sort of retirement project. And the two of them have a house right next door to this observatory, the Weiner Observatory in Sonoyta, Arizona. And our Iowa Robotic Observatory, our Gemini telescope, isn't the only telescope on site. There are other telescopes. There's one operated by NASA. There's one operated by a university in Poland. There's a couple of telescopes operated by the Ohio State University. And so there's a number of different sort of customers who use the Weiner Observatory, and the University of Iowa's Iowa Robotic Observatory is one of them. And every night, these site managers, their names are Mark and Pat Trueblood, they're checking to make sure that everything is going well at the Iowa Robotic Observatory and the entire Weiner Observatory facility. And one thing that they have set up to do automatically each evening is that the roof will roll off of the observatory. And so, in this picture that I've shown you all before, this here is the roof. I believe you can see my pointer, and this here is the roof. And it's actually currently like a double roof right there because the roof has rolled off at this point. But during the daytime, this whole roof goes to the right during the daytime to protect all the telescopes that are here. And this roof rolls off every evening automatically. But I did see, as Professor DeRoo was talking, on our little camera, which I know you've seen before down here, I saw that the lights were on and, you could tell someone was walking around in the background. And I contacted the site manager, Mark Trueblood, and he shared that, something was up this evening and the roof didn't roll off when it was supposed to at the correct time when the sun had set and it had set sufficiently. The roof will usually roll off automatically, but it hadn't. And it looks dark in there now, so I'm hopeful that the roof has either rolled off or will soon be rolling off. But in addition to a little bit of cloudy weather potentially tonight, there is also this new detail about if the roof is behaving. But let's say a little bit more about the observatory, and then we will check out to see if we can catch anything on the sky. As many of you now know, just to review, on the right-hand side of this picture is where our Gemini telescope is located. And the Gemini telescope is made by a company called Pinwheel. They make some fantastic telescopes. And this is their 20-inch model. So it's a half-meter telescope. When we say a half-meter telescope, we mean that the main primary mirror that first collects light from the sky, the part of the telescope that light first touches, hits, interacts with, is this giant mirror on the back of the telescope that's a half-meter across, or 20 inches. And this 20-inch telescope, as all mirrors do, the light bounces off of that main mirror, and it travels up top and it hits this secondary mirror there. This telescope company, Planewave, they really specialize in what are called CDK telescopes, or corrected Dahl-Kirkham telescopes, which means that the primary mirror is shaped like an ellipse. The primary mirror is elliptical, that one down at the back of the bottom, and the secondary mirror is spherical in shape. The light will bounce off of that secondary mirror, travel along the telescope, and then that primary mirror actually has a hole in the middle of it. And so light can, after hitting the secondary mirror, pass through. And it will encounter the filter wheel. A filter wheel is a way to take all the light that's coming from the sky and select just the blue colors of light, or just the green colors of light, or just the red colors of light, or just the colors, just the wavelengths of light that come from particular atoms. Maybe you just want to view oxygen of a particular target that you're looking at, or you just want to view particular types of hydrogen light. That can be very interesting too, rather than just grabbing the blue colors or the green colors. What if you want to grab the light that comes from a particular atom out there in space in the object that you're studying? We can do that by putting a filter in the way of the light and blocking out all the light except for the colors that you're interested in. And then light will touch the CCD camera, which collects the photons of light, the particles of light, and turns that information into an electrical signal, an electrical current that through wires is routed back to our computer so we can see the images that we took. A mount points the telescope around in the sky, and we also have a focuser on the telescope to get nice, sharp, bright images. Someone in the chat asked a question about how this telescope differs from the telescope that we have here on campus at the Van Allen Observatory in downtown Iowa City at Van Allen Hall. And they're very similar. They're made by the same company. They're almost the same size. In fact, the reason why the telescope in Arizona is called the Gemini telescope is because these two telescopes were designed to operate very similarly, almost identically, sort of as twins, the name Gemini being like the Gemini constellation of the twins. And so the telescope on campus is actually a 17-inch, so a little bit smaller, but you know, exact same company, the optics of the telescope work the exact same way, and very similar sizes. All right. So our first target for tonight is going to be the Sombrero Galaxy. Oh no, I just got an email saying that the observatory is closed for the night. If the weather is too bad or if there's a problem, we'll receive emails, you know, just letting us know. So I'm a little nervous that when we get to this target, either the roof isn't going to have been opened, so we won't see anything, or you know, maybe the weather is just really bad with clouds, and that's why they decided that the observatory won't open tonight. So it might be weather, it might be technical difficulties, but regardless, we can still look at some pictures that we took, you know, the night before last and the night before that, just to make sure that everything was ready to go for tonight. So let's see. I will just do a very quick image. Pick a red filter. Just see if we see any stars just to start out.
I have a pretty funny story about the telescope while we're waiting.
Yeah.
Last year for lab, we had to go point and to do like a specific project or something like that. And my project was to look at all the different types of the spectral classification types. You had to point at like an O star, B star, stuff like that. Me and my group. and then you got to you got to like code like the little block of like the coordinates you want to push it at, like the specific time, the exposure, everything like that. And then we did our block, and then sent it to our friend's email, and then sent it to another guy's email just as a joke. We were just messing around with him, and so he'd just get these random star photos and didn't know what was up. And then we closed out of it as the lab was over, and then the next lab, we just made a new one without thinking, and the new like block of code wouldn't work. And so for about a month, actually, we would never get our star pictures, and we didn't know why. And it just turned, it's because we already like coded the first block, and so this poor guy on campus was just getting a photo of stars every day for a month, just sent to his email.
Oh gosh. Awesome.
And he didn't know who to like report it to or anything like that. He just and we couldn't do our lab or like proceed or anything like that because we just messed up. And needless to say, our TAs weren't very happy with us. But the project ended up getting done. That's what counts. That's my telescope story, the Gemini.
And that's really one exciting thing about the University of Iowa is unlike some colleges and universities, there really is the opportunity for hands-on experience with these two telescopes. Students are using them. They're really getting real data to do their lab projects and so on and so forth.
Even if you're not in the group.
Yeah. Tonight on the sky, there are a lot of galaxies that are visible in the night sky. What you have on this image here that shows tonight the night sky, the white dots are stars, the purple circles with little X's through them are star clusters, but these yellow ovals are galaxies. And you can see we have a fair amount of them over here in the west, the western half of the sky in particular. And you'll see a real clumping of them, a really big concentration of galaxies in this general area. And this is actually near the constellation Virgo, the Virgin. And there is this Virgo supercluster of galaxies. And so again, in the direction of the constellation Virgo, stars in our Milky Way galaxy that are in a particular direction in the sky. Back behind that, outside of our galaxy, there are all these other galaxies in a group. And we're a part of that group, but we're kind of on the edge, and we can see all of these other galaxies in that particular direction, in the direction of the constellation Virgo, the Virgo cluster of galaxies. And so there's actually a ton of galaxies in this grouping right here. But that being said, there are a lot of galaxies up in the sky that can be observed. Let's go ahead and take a look at what is up in the sky tonight. So again, if there weren't this mechanical issue with the roof, one object we could look at is the Sombrero Galaxy. So the Sombrero Galaxy is located in the constellation Virgo, and it is 31 million light years away. On the left here is an image of the Sombrero Galaxy that Cole and I took the other night, a couple nights ago, with the Iowa Robotic Observatory. And on the right is an image of the Sombrero Galaxy taken by the Hubble Space Telescope. Another galaxy, that Sombrero Galaxy, was a lenticular galaxy, partway in between a elliptical galaxy and a spiral galaxy. And another lenticular galaxy that looks a little bit more elliptical, maybe than the Sombrero Galaxy did, is this Messier 85, which is in the constellation Coma Berenices. It's about 60 million light years away. And a very cool thing about M85 is just a few days ago, a supernova was discovered in it. So in this other galaxy, there are tons of stars, and one of those stars died and went supernova. And astronomers here on Earth were just observing galaxies and noticed that there was a brightening that isn't usually there, isn't supposed to be there. And so, you can see here's the center of the galaxy. Here's a bright star that's nearby. It's probably a star in our own Milky Way galaxy that is just in that direction, and it kind of like photobombs. It's not actually a star in M85. It's just a star in our own galaxy kind of blocking the way. But next to that photobombing star is a bright little dot. You can see it there, but I zoomed it up. I blew it up for us here. And that little dot is a supernova. It's not usually shining there. It only just started a few days ago when that star died. And it will continue to shine for a number of days, but then over the course of many weeks, many months, it will disappear. It will dim over time. Once the explosion has occurred, the black hole or the neutron star is still there, but you can't always see the light from the supernova a few weeks or months later. Messier 61 is a barred spiral galaxy. It's also in the constellation Virgo, very possibly part of that Virgo supercluster. It's 53 million light years away. On the left, we have an image taken with the Iowa Robotic Observatory Gemini telescope a few nights ago. And on the right, we have an image of Messier 61 taken by Hubble. There is also the Pinwheel Galaxy up tonight. Messier 101 is in the constellation Ursa Major, or the Great Bear. It's 21 million light years away. You can see the spiral arms of the galaxy, right? Sweeping outward. Messier 83 is the southern Pinwheel Galaxy, and this is a barred spiral galaxy. So you can see spiral arms, certainly, but there's also this straight bar through the galaxy. The southern Pinwheel Galaxy is in the constellation Hydra, the water snake, and it's 15 million light years away. So getting a little closer, probably one of the closest ones we'll mention tonight. The Black Eye
I'm sorry.
Galaxy.
I want to stop you before you go on. Just some other things about the southern pinwheel that I learned.
Oh, yes.
That it rotates on its edge 508 kilometers in a second, which is quite fast.
Yeah.
Pretty average, I bet, for a galaxy. It's also the first galaxy to be discovered outside our local group. It's the first farther away galaxy. It's still relatively close, but out of the ones that are super close to us. That was all. I'm sorry to interrupt you there.
Oh, no, that's perfect. No, just knowing more information about these is so wonderful. The Black Eye Spiral Galaxy, Messier 64, is also in the constellation Coma Berenices. It's 17 million light years away. Again, Iowa Robotic Observatory image on the left, Hubble image on the right. Messier 82 is the Cigar Galaxy. It's in the constellation Ursa Major, the Great Bear, and it's 12 million light years away, so also pretty close. This irregular galaxy that actually I don't know how recently it was, but some point in the somewhat recent past, astronomers discovered that it actually does have two spiral arms. So this galaxy is technically a spiral galaxy, even though it looks a little funny. It really definitely looks a little bit more irregular, like an irregular galaxy, and for a long time it was classified as an irregular galaxy. The Cigar Galaxy is actually very close to Messier 81, this Bodes Galaxy, and we actually observed Bodes Galaxy on our first night of these observation nights. It was a request by an audience member, two audience members actually. Bodes Galaxy is probably one of the closest galaxies to us up in the sky right now. It's maybe about 6 or 7 million light years away. And I also forgot to mention last night we viewed the Ring Nebula, and that was actually a request by audience member Wendell Clifton. So thank you for these requests. Messier 63 is the Sunflower Galaxy. It's in the constellation Canis Venatici, or the Hunting Dogs, and it's 29 million light years away. And that brings me to the end of the objects that we were hoping to observe tonight. A lot of different spiral galaxies often look the most impressive on camera, but we also included this elliptical galaxy, the sort of lenticular, sort of elliptical galaxy Messier 85 that had that recently discovered supernova. We have a few minutes left. We could maybe stay on and answer a few of those questions, either live or via the chat, but formally, I would want to end our program now. I want to say thank you again to Cole and Professor DeRoo, and most importantly, thank you to each one of you for coming out to these observing nights. It's been so wonderful to have you here, and we're so glad that you could join. Feel free to sign off now. Cole and I will stay on for a few more minutes, and we can answer a couple more questions until 10:30, either live or in the chat. But thank you again.